In this video, I am going to discuss about extrinsic semiconductors. When intrinsic semiconductors are used for developing semiconductor devices, they have many limitations as discussed below. Intrinsic semiconductors have low intrinsic charge carrier concentration of hole and electrons approximately equal to 10 power 6 per meter cube. So they have low electrical conductivity. An intrinsic charge carrier are always thermally generated, so flexibility is not available to control their number. For intrinsic semiconductors, number of electrons is equal to number of holes generated in the process. They cannot have predominant hole or electron conduction. This puts a limit to the usefulness of intrinsic semiconductors. Now we are going to discuss about the process of doping and the essential requisites of doping and the various methods of doping. In order to increase the conductivity of pure semiconductors and to overcome their other limitations, a small amount, say 1 part per million of impurity atoms having valency different from 4, that is tetravalent, is added to the pure semiconductor. This process of deliberate addition of a desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. The impurity atoms added are called dopants, and the semiconductors doped with the impurity atoms are called extrinsic or doped semiconductors. I am repeating again since this is an important point. The process of deliberate addition of a desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. The impurity atoms added are called dopants, and the semiconductors doped with the impurity atoms are called extrinsic or doped semiconductors. The essential requirements for a doping process as below. The semiconductor material should be of very high purity, 99.99% or more. The dopant atom should neatly replace the semiconductor atom. The size of the dopant atom should be almost the same as that of the semiconductor atom. For this, the atoms of third and fifth group of the periodic table are mostly suitable. The dopant atoms should not distort the crystal lattice. Again, I am repeating, the size of the dopant atom should not distort the crystal lattice of the existing semiconductor atoms. The concentration of dopant atoms should be small, about 1 part per million. So, based on the impurity atoms added to the semiconductor, there are two types of dopants used in doping the tetravalent, silicon or germanium. The first one is pentavalent dopants. They have 5 valence electrons. For example, arsenic As, antimony Sb, and phosphorus symbol is P. The second one is trivalent dopants. They have 3 valence electrons or 3 free electrons in their outermost orbit. For example, indium, boron, and aluminium. On doping silicon or germanium with pentavalent and trivalent doping impurity atoms, we get 2 entirely different types of semiconductors called N-type and P-type semiconductors respectively. Methods of doping. By adding the impurity atoms to an extremely pure sample of a molten semiconductor, we can dope the semiconductor. The second process is by heating the crystalline semiconductor in an atmosphere containing dopant atoms or their molecules and third one by bombarding. Thank you.